Hi, welcome back. This is Module 3. This lesson is about the normal model. The normal model is a crucial concept in a statistics course. The ideas and skills you learn through working with the normal model will show up in pretty much every lesson after this one. So I encourage you to listen, watch carefully, rewind, pause, whatever it might be, so that you can better grasp the knowledge we'll learn in this module. I think the best thing we should do to introduce the normal model is to start with an example.
So I chose to look at the pulse rates of 300 randomly selected U.S. women between the ages of 20 and 55. Now, I represented these women and their pulse rates in a histogram, as you can see. Now we can see from the histogram that the horizontal axis is beats per minute, so that's where the actual pulse rates reside, and that our vertical axis, as with any histogram, or I guess with this one, represents the number of females that fall into each of these different intervals of pulse rates. So if I look closely at the numbers along the horizontal axis, I can see that they appear to be at the right side of every bar that they're labeled on. And so that implies that these are right cut points. So here I have my cursor here at 99. Let's take a look at there. So what I see is that if this is labeled here at the right part of this bar as 99, that means that everything to the left, every part of these bars to the left, are considered less than 99. So it's kind of a convenient way to label a histogram. So let's see. We can see that there's a big mound here in the middle, a central hump we might call it, and that I would say that most women among these 300 have pulse rates somewhere between, let's say, 67 beats per minute as the axis tells us, and maybe up to the mid-80s here, 83, 85 beats per minute. And we can judge that because of the height. These bars are a lot taller than the rest of them. And with less frequency, we're going to see women with extremely high pulse rates up here, above 100. And likewise, down in the lower numbers here, we're going to see less frequently did we observe women who had slow pulse rates back in the 50s. So let's start off and answer a question concerning this histogram. What percent of women have pulse rates less than 51 beats per minute? Take a minute, examine this, and see if you can come up with a solution. Let's take a look at the histogram. If we look across the horizontal axis, we can see that 51 here is our first right-hand cut point. So if we're trying to find what percent of women have pulse rates less than 51, we have to determine how many women are in this bar that's to the left of 51. Now, the vertical axis isn't perfect. It only goes up in steps of 10, but I think we can get a good guess, or what we might call estimate, for that height. If you said 6 or 7, we'd be in agreement. Let's stick with 7. 7 women among these 300 have a pulse rate less than 51 beats per minute, this extremely slow pulse rate of 51 beats per minute. How do you determine that percent? It's not too terribly tough. There it is, our height that we're looking at there with the arrow. 7 of 300. So 7 divided by 300, we see the decimal there of 0.0233. And we quickly turn that into a percent by multiplying by 100%. So only 2.33% of women among these 300 have a pulse rate of 51 beats per minute or less. So I'm not too terribly surprised by this outcome. We can see that it's a rather short bar. It's only one bar in our histograms, a small proportion of women. And in general, not many women have pulse rates less than 51 beats per minute. It's an extremely slow pulse rate. So 2.33% is our answer. Before we leave this histogram, how would you describe it? Think back to Chapter 4 and some of the words we used to describe histograms. Well, let's see. I think we can all agree that it's unimodal. There's that one central hump here in the middle of the histogram here. And we also, beyond describing how many humps the data has, we also like to talk about the general shape of the data. And it looks like it's somewhat symmetric. It's not perfectly symmetric, but I would describe this as maybe roughly symmetric or somewhat symmetric. Some people might argue that there's a little skew to the right here, and they may not be entirely wrong, but overall, I believe this histogram is unimodal and somewhat symmetric. So, we have our histogram here, and what oftentimes happens is that statisticians, or software in this case, will draw a smooth continuous curve over the histogram. Now this curve is there to represent the general shape and spread of the data, or we might call distribution of the data. And you can see that it's not perfect. It's a little short for some bars. In other words, the pink bar might be well above the blue curve. And it's sometimes a little high for others. So it's not a perfect thing, but it does a good job of, in general, summarizing what's going on with this specific histogram. Now, the next step that we typically do is we remove the histogram altogether. Just remove it. And we're left with describing the pulse rates of these 300 women with just the blue continuous curve. Now, we can still see what's going on with the data. We lose a little detail, I have to admit, but we can still see that the central mound here we talked about earlier is here between, like, say, 67 and 83, and we can kind of see that there's that tapering off to the right as well as the left. So we still have an idea. And remember that we can judge the center of the distribution by looking directly under the peak, the mound. So I would say that the more typical, say, average pulse rate, and the mean pulse rate of these 300 women is somewhere between, let's say, 74, 75 beats per minute. So we don't lose anything by removing the histogram. We're actually doing something called applying the normal model. This is where the normal model comes in. This bell curve shape that we see that was a good description of the pulse rates shows up over and over in statistics, whether we're talking about pulse rates or the length of bones, or sometimes finance. It's amazing. It comes up over and over. A lot of data has this roughly symmetric unimodal look to it. And this model is so widely used that they came up with a name for it called the normal model. And it is a way of summarizing what's going on with the data. So instead of trying to when we try to find percents and some generalizations about the data and using sort of the jagged stair step of the histogram, it's easier for us to talk about that blue curve and talk in general terms about pulse rates using that smooth blue continuous curve. And again, this idea of the normal model is only appropriate when we have this type of data, that is unimodal and roughly symmetric.